Hi, everyone. I'm Phil Koopman. I've been doing self-driving car safety for just shy of 30 years at this point. The origin story is just before I started doing it, Carnegie Mellon University had a self-driven car. It was mostly a lane-keeping system that went from Washington, D.C. to San Diego, 98+% hands off the wheel. And ever since 1995, the industry has been working on that last 2%. And so that's half of it. The other half is once you get the cars out there running around and they're pretty good at for 10 cars, say, and they're running around. Some people might say that's the first 90% of the effort. But in fact, safety and scalability is the other 90% of the effort. And people are just sort of waking up now to the scale of what it takes to get past the really cool demo and pilot into full-scale production. And I'm here to talk about that because safety sort of comes in. I mean, you can have mishaps during testing, but safety, really, the big problems with safety show up when you try and scale. And I'm here to tell you that by the end of this talk, I hope to convince you that what you thought was safety for most of the audience, what you thought was safety is probably only a little tiny slice of the safety pie that really needs to be addressed if you want to operate with 100,000 or 1 million vehicles. So we're going to start by talking about understanding what safe enough means for autonomous systems. And it's grounded in self-driving car experience, but this is a more general talk. This is not just about self-driving cars. The things I'm talking about end up mattering for anything that's autonomous, but this is, for the most part, a robotaxi talk, to be sure. And it's more than positive risk balance, and we'll get into exactly what the details are. And I think the second half of the talk, so the first half is explaining why it's different. The second half is explaining how we should really be thinking about safety. And it goes beyond net risk minimization. In fact, it changes how people have to think about safety. Typically, safety engineers think about, well, engineers in general are trained to be optimizing. Engineers all like to optimize, and they're trying to minimize risk. But minimize risk gets you only 1 out of 7 points for safety. It turns out that an optimization formula probably will not work. And instead, you need to treat this as a constraint satisfaction problem. And we'll get there. By the end of the talk, you'll understand why I say that, but that's where we're going in this talk. Before I dive into what safe enough means, let me talk a little bit about the V model in machine learning, because this is the reason why everything has to change. Safe machine learning and autonomous systems break the V model. Now, the V model, for those of you who've seen safety standards or automotive engineering, this is a pretty classic thing. You have requirements down the left-hand side, and then you have an implementation, and you do verification, mostly validation on the right-hand side. And the idea is for each piece of the design process going down the left, there's a corresponding set of tests that validate it. So the detailed design might be tested with unit tests, and the requirements are tested with more system level tests. And the important part is this does not necessarily work the way many people act. Many people act as if, well, you do the design down the left and the testing is there to prove it's safe. That's not true. The testing is not there to prove it safe because, well, if you ride in an airplane, they did not fly the airplane for 1 billion hours with a B, because that's the requirement. They did not fly the airplane for 1 billion hours or 3, seeing if it fell out of the sky, and then, only then, letting passengers on because it was safe. They don't do that. So the testing there isn't a brute force testing for safety, and it shouldn't be that way for cars either, because that will never work for software. Instead, what happens is, when you follow a rigorous engineering process, the fact that you followed the rigorous engineering process sets a strong Bayesian prior expectation of correctness and of safety. And the validation is not there to brute force test everything. The validation is to confirm that the engineering process was properly executed. And mathematically, this ends up that if you have a strong Bayesian prior, you need a lot less evidence to support the conclusion than if you have no prior expectation. You just say, well, let's just drive around and see what's happening. The problem is machine learning breaks the causal linkages between the design and the validation. You can say, I have a bunch of requirements, but then you test and you say, well, you train, you say, well, I'll just train a bunch of road data. That road data has nothing to do with your requirements unless you're clever, and that's why people have things like the Pegasus project with scenario-based. I get that, but assuming you're not being smart like that, you just drive around to see what happens and then say, all right, when you're doing that, road testing is not has no strong Bayesian prior. It has no Bayesian prior at all. It just says, well, we trained some stuff. Let's see what it does. And it takes a lot more testing to the point that it's impossible to test that much. Nobody can afford it. And so machine learning breaks the causal relationship between the design process and the validation. And that's why you see things like a scenario-based approach. You see some safety standards. You need to follow the rigorous safety standards and process standards to have a strong prior expectation of safety, or else you need more testing than you can afford. Now, people will say, oh, that's fine, we'll just brute force it in simulation. But all that does is push the engineering burden onto the simulation. How do you know the simulation is complete? So this will come back in one of the issues, but I just want to point out that this is a fundamental reason from a technical basis why machine learning and self-driving technology is hard to do safety for. It breaks the existing paradigm for safety. There's also a social reason, which we'll get to in and out, but the social reason is we're used to having a driver to blame for crashes. And in an autonomous vehicle, there's no driver to blame, and that breaks a lot of other stuff. We'll get to all that. Okay, so let's go into what we mean by safe. What do we mean by safe exactly? Here's a picture of a Cruise robotaxi entering a construction area. You can see there's a flagman, there's a bunch of signs saying do not enter, road closed, but it went in anyway. And I suspect, but not sure, I suspect a remote operator was behind what happened here. But is this safe? You know, is it safe to have a robotaxi wandering around a construction area? Well, no one got hit, no one got hurt, no one got killed. So there was no safety report. It does not show up in the safety statistics. So at the time, Cruise was claiming that there were multiple safer than human drivers, and yet this happened. This did not affect their statistics. So maybe safety has a little bit more to do than just the body count of how many people who are hurt or killed. How about statistical parity? What if you are as safe as an average driver? And the US has a terrible drunk driving problem. A large fraction of our fatalities are associated with drunk driving. Is it okay to be as good as an average driver, including all the drunk drivers? You know, maybe you'd like better than that. So even if you just say, we're going to just count up the number of injuries and fatalities, and then that's our goal, that goal is table stakes. It's the starting point. It's not the ending point. And what I'll do, I have one slide on each of these topics coming up, is I'm going to talk about all the things you need to consider beyond just as safe as a human driver. And hopefully by the end, I've convinced you that you need all these things. And the second half of the talk will explain a way to look a little bit differently about safety to support that. So the first is positive risk balance. When you hear any of the autonomous vehicle companies talk about safety, what you're very likely to hear is, well, we're going to be safer than a human driver, maybe just as safe or maybe safer. And they say we're safer than a human driver. And that's called positive risk balance. Now, when they say that, what they really mean is statistical, right? It's the number of people who are hurt or killed. But even doing that, you may have seen on the first slide, I have a book called I'll show it up. I have a book on this, right? So there's this book I have, and it shows up, right? How safe is safe enough? Okay, this slide is this book in one slide, and the rest of the talk is what I learned after I wrote that book, just so you know where I'm coming from. Okay, fine, safer than human driver. Which human driver? Are we going to exclude the drunk drivers? In the US, it's 28%. US has horrible traffic safety compared to most countries in Europe. It's 28% drunk driving, 26% speeding related. Distracted, everyone says that's the biggest problem, but it's only a 10% problem for fatalities. Surely it's a problem, surely it should be addressed. But in fact, it's like a 9% problem, last numbers I looked at. And there's also a 3.5 times spread between a 60-year-old driver and a 16-year-old driver. It turns out people would say, well, computers are going to be better drivers because they have fast responses. Well, I know for sure that 16-year-olds have a faster response time than I have, but the data shows I'm a much, much, much safer driver because it turns out that experience and knowledge and contextual awareness is much more important than fast reaction time in humans. And so when people say, well, computers are fast and old people are bad drivers, the data does not support that as a reason for computers to be safe. And who and where. So if you go to different states in the US, there's a 3.4 times fatality per mile traveled variation from state to state. If memory serves, Massachusetts is the safest despite having Boston in it. It's a really safe state. Among other things, they spend a lot of money on road infrastructure, apparently. And I think it's South Carolina is the most dangerous one. So when you say I'm as safe as an average driver in an average car across the US, you may have, perhaps a factor of 10 difference between where you should be, because you're in a place that all the other drivers are older and all the other drivers are safer, and they're all driving new cars. The average car in the US is more than 12 years old. So if every car were a robotaxi today, it would be more than a decade to even get half of the cars on the road that way. But also those old cars don't have the safety features. So every new car is safer than an old car. Every robotaxi, by virtue of being a new car, is automatically safer than an average car simply because it's a new car. So if you really want to be safe, you should be comparing yourself to a middle-aged driver who's not drunk, who's in a comparably new car, and that is dramatically more safe than the average. So when you say safer than average, it's almost meaningless. You have to be a lot more careful. Okay, the next part of safety. Let's say that you know how to be as safe as a comparable driver in a comparable car in the comparable city, and the newer robotaxi safety statistics are in fact getting sophisticated that they're trying to take all those things into account, which is great. Let's say you get there. There's other aspects to safety. Now I'm going to give you some hypotheticals, and it is not my intention to say this will actually turn out. I think it's unlikely to turn out this way, but I'm giving you hypotheticals because if you think these things matter, then you're disproving the notion that net statistical safety is the only criteria that matters. So what if children are at greater risk, or disabled pedestrians or bicyclists? So let me show you a news story headline, and I'm going to caution this headline is somewhat misleading. So I'm showing it as an example, not saying it's true. But there was a news story saying crews knew its self-driving cars had problem recognizing children and kept them on the streets anyway. And the hypothesis was they were driving around at 1 a.m. because they figured there'd be no kids, so it didn't matter if they didn't see them. I think there's more to that story. I think it's more nuanced. I think that the author of that story could have benefited from a better understanding of how hazard logs work and how risk mitigation works. But look at that headline. That headline's a problem, right? What if it were true, hypothetically, I'm not saying this is true, what if it were true that it's about 40,000 fatalities in the US? It sounds like a huge number, but there's a lot of Americans and we drive a lot of miles. But what if it's 40,000 is a round number for the US right now, and that went from 40,000 to 20,000? From a positive risk balance, you cut the number of fatalities in half, and that's a win. What if all 20,000 of them were pedestrians, which would be more than a 3 times increase in the number of pedestrian fatalities? So you have nobody killed inside a car, and you have 3 or 4 or 5 times as many pedestrians killed, but the total number of fatalities went down. Well, positive risk balance says that's safer. But if you're a pedestrian, you probably have an issue with this, right? I don't think that would be okay, that especially since the people benefiting from the technology now have no risk whatsoever, and the people who are not benefiting from the technology, who aren't affluent enough to buy taxi rides and have to walk instead, they're the ones at dramatically more risk so the other people can benefit. I think that's going to be a problem. So I think that any vulnerable group that is put at a markedly increased risk from a technology is not going to be acceptable. And so if you reduce the average risk, that's table stakes. You have to do that. But you also, at the same time, have to make sure that other vulnerable groups are not put at elevated risk for the benefit of those using the technology. That's an additional constraint on safety. Another one is negligent driving. So I have 3 law journal papers now. That is 3 more law journal papers than I ever expected to have in my life. But I met a very, very smart lawyer at University of Miami, and we co-authored some law journal papers about negligence and robotaxis and autonomous driving. And so this is the layperson, I'm not a lawyer, this is a layperson understanding of what's going on here. But when you drive a car, you're doing something that is inherently dangerous. And because it's inherently dangerous to other people, you have a legal obligation to try to make a reasonable effort. Reasonable is a tricky keyword for legal. You have to act as a reasonable person to avoid hurting other people. You're not allowed to go around and run over people on purpose. In fact, you have to make really strenuous efforts to avoid hurting other people because you're doing this dangerous activity. And so that's called having a duty of care. You have a duty of care to other road users to avoid hurting them to a degree reasonable. Nobody's perfect. There will be crashes, but you can't be reckless. You have to really pay attention and really make a best effort to avoid hurting anyone else. So if you fail to make that effort, if you don't pay attention, if you're distracted, if you're drunk, if you're running red lights, you have violated the duty of care because you're being reckless or negligent. The word is negligent. And so when you hear about U.S. law, U.S. has these big tort law cases where millions, tens of millions of dollars get awarded because somebody was a reckless driver and someone else got hurt. That's negligence, all right? Now, I should set aside, since it's a mostly European audience, in Europe, you don't have those laws, but you also have type approval. So there's a presumption the vehicles are safe before they go on the road. In the U.S., there is no type approval. Anyone can put any car on the road they want by self-certifying with a sticker saying, yeah, it's fine. And the federal government only comes in later. And to counterbalance that freedom, we have a stronger legal system that has bigger fines for acting recklessly, because you either have to have front-end approval or you have to have back-end legal pressure. If you have neither, you're not going to get safety. So we just work differently. So Professor William Wyden and I have proposed that a computer driver, the computer in robotaxi, should have a duty of care the same as a human driver. And what you should ask is not, is the robotaxi perfect? People want to hold computer drivers to perfection. And while that's a nice goal, I think it's impractical. But what you can do is say, let's pretend it's a human. And if the human had been negligent, the computer should be negligent. And that pivots you away from product liability into tort liability. There's a lot of benefits that come, and if there's any lawyers in the audience, we can do questions on that later. But we have a whole set of write-ups on this. We think this is really important. Right now in the U.S., the computers do not have a duty of care. So there is no law requiring a computer to avoid running over other people. And in some states, there are laws that make it very problematic to enforce that if a computer runs someone over. In one state, the only thing you can sue is a computer, which is not a person, doesn't have assets. This is really a problem area in the U.S. Now, what does this turn into safety? Well, if you're a designer, how do you take action? People historically say, well, we're safety people, we don't do legal. Well, when there's no human driver there anymore, you sort of have to take legal into account with safety, because the computer is what's going on here. But let's look at how this works in practice. Hypothetically, let's say I've done 1 billion with a B miles and I've never killed anyone. Statistically, I should have killed 10 or 11 or 12 people, depending on the state, and a bunch of other stuff, but maybe a dozen people after 1 billion miles, and I haven't killed anyone. That does not give me a free pass to run red lights and disobey traffic laws. I'm a safe driver, so I don't have to pay attention to red lights is not a good thing, right? You would never be happy with someone who said, I'm such a good driver, rules are optional, traffic rules don't apply to me. Okay, you still get the speeding ticket, and if in heaven forbid you should kill someone after running a red light, you can and should be prosecuted the same as everyone else. The fact you have 1 billion miles without killing someone does not give you a free pass. Well, what if you have a robotaxi company that says, we're saving lives? On average, we're safer, so you should forgive this horrific mishap where our robotaxi did something that a human driver would never have done, broke laws, did all these things, but you should forgive us because we're saving lives. It's the same argument. And so what you're going to find out is that robotaxis have to avoid negligent, reckless driving the same as human drivers, and the fact that they are statistically safer, assuming someday they can prove that, does not enter into it. They're not allowed to be reckless even if they're saving lives. That's an additional constraint. Number 4 is that we're going back to that V picture I had, that the reason we're safe is not because we tested a lot. The reason we're safe is because we had a strong prior expectation of safety, and the testing was to validate that expectation. Well, how do you get that strong prior expectation of safety? The only way we know how to do it is by using engineering rigor, or proven in use, but proven in use doesn't work for new technology. So it's engineering rigor. Well, the way we get engineering rigor is we have standards. And for this crowd, I'm not going to read and explain every single standard, but there's standards for cybersecurity, for functional safety, for the dynamic driving function, for system safety. There's one for a safety case. So ANSI UL 4600 tells you how to evaluate a safety case. And there's some new ISO standards. There are all these standards. So if you wanted to have a strong expectation of safety before you got on the road, you would conform to these standards. That's what they're for. These are written by the industry for the industry consensus standards. Right now in the US, these are the only standards required. All the rest are optional. And in Europe, it's not so different. I expect that's going to change in Europe before it changes in the US. But right now we have an industry which has traditionally not really conformed to their engineering standards. And they've been able to get away with it because they have a lot of older engineers who have a lot of experience and know what they're doing. They sort of grew up from the first days of computers, but those guys are retiring. But the other reason is that when something goes wrong, they can blame the driver. So if there's an equipment malfunction in ISO 26262, you use controllability to say, well, yeah, that could malfunction, but the driver can compensate. And so drivers get blamed not just for making mistakes, but also they get blamed for failing to compensate for an equipment failure. Well, that's all well and good, but when there's no human to blame, what's your plan here? And so the switch to pulling out humans really forces another look at these standards. And the industry has been very reluctant, very slow to adopt these standards. They will say they're working on them, but there are few companies, very few. It's rare to find people saying, yeah, the entire robotaxi, robotruck will conform to all these standards. So I'm going to say probably you need to conform to the standards to set a prior expectation of safety. The next one is fine-grained risk in regulators. When you say net risk, so positive risk balance is statistical net risk. But the problem with that is that recalls and other fine-grained risks are not about statistical. Now, we already saw this a little bit. Remember I said vulnerable groups cannot be at higher risk even if everyone else is at lower? There's another one that when you have a regulator and they do a recall, the regulators recall on risk, but they do not recall a net risk. So I've never seen a recall on, well, this car just crashes too often, and so we're going to recall it. The recalls are for specific defects, not risk. So here's some recalls we've seen on level 2+ vehicles that have human supervised automation, so supervised automation. And what we saw was a recall for rolling through stop signs. And so the company had automated the process of saying, well, there's a stop sign there, but I think the intersection is clear, so I'm just going to roll through it. And they weren't rolling at 1 kph. They were rolling it faster than a person walks. They were running it at like a jogging speed. It was actually quite fast. And if the computer were wrong and it hit someone, they would blame the driver for reckless driving. So there was a recall for that. There's been recalls for many different recalls on phantom braking. That's braking when there's nothing really there, but you put on the brakes and someone hits you from behind because they knew nothing was there and they weren't expecting you to brake. And also lots of malfunctioning display consoles. There's so many rear view camera recalls, but also the main console with the current speed and malfunction indicators, those things die. But none of those are your car's unsafe net. Those are this specific aspect. Your car keeps hitting emergency vehicles because they have flashing lights. Go fix it. And so these are specific defects, usually behavioral of some sort, and with specific fixes. So, and they're by definition safety. It says right there, Part 573, Safety Recall Report. If you have a recall, you are by definition having a system that's unsafe that's being fixed to make it to get rid of that unsafe issue. So that's another aspect of safety. Even if your statistical net safety is okay, you will get recalled if you have a behavior that's a problem, and saying, but we're saving lives does not protect you. And I will note that software quality net risk are not something the regulators have looked at. That has to change because there's no longer a human to blame, but they're still working on that. The regulators really need to move aggressively into the software realm, which they're starting to do, but historically they'd spent a long time not doing that. Number 6 is ethical and equity concerns. Ride-hail made promises. Robotaxis are making pretty much the same promises Ride-hail made, and Ride-hail failed to deliver on most of those promises. And robotaxi companies are there to make a profit, so I don't know why people expect it will turn out any differently in the 10-year time frame when they're done putting on a show to make everyone happy. Long term, are they really going to deliver? If the regulators don't require it, there's no reason to believe that will happen. So some of the issues we're seeing are that it used to be taxi drivers were afraid that ride-hail drivers would displace them. And yes, in fact, a lot of that happened. Now the ride-hail drivers are afraid that robotaxis will displace them. And assuming the technology is scalable with acceptable safety, yeah, that's probably going to happen too. The truckers have similar concerns, although we're earlier in the process. People say, well, the robotaxis will give disabled people more freedom. Will that really happen? I mean, people still have to pay. And for example, right now, we're still seeing for a long time, the wheelchair access robotaxis were actually human driven because you still have to help the person get in the cab. There's a lot of questions. The robotaxi people sell on helping disabled, but a lot of that is more sales than technical reality. We're gonna have to see how that happens. There's a really interesting system level issue here that a normal human-driven taxi, and a lot of taxis are safer than average drivers. It depends on the data, but I've seen cities where the taxi drivers are much safer than the drivers before ride-hail days. So even if you put someone in a safe car, they're perhaps a factor of 10 more dangerous than mass transit. And so if robotaxis draw passengers away from mass transit, which is what ride-hail did, and there's every reason to believe robotaxis will do that as well, unless there's a business model compensation to avoid that. If they're pulling riders out of mass transit, not only does that degrade mass transit ability because of funding, but it also makes safety worse because each mile in a car is more dangerous than a mile in a train. And so you could see robotaxis that are dramatically safer than humans still result in a higher fatality rate for a city because they're pulling people out of more safe transit into less safe transit just because the individual cars aren't as safe. There are also ethical concerns. People say, well, we're going to save lives someday, so you should ignore the loss events we have now, which isn't a really ethically fraught argument. But also, there's no required independent technical safety oversight in the US. I know Europe has type approval, but I think they're still struggling with how they're actually going to vet these things because the road test doesn't prove it's safe. A road test just proves it's not really dangerous. And the companies right now are the ones who decide when it's time to pull the safety driver. I know in Europe, it'll be a little more overseen, but that's going to be a really tough thing to pull off safely. So there's a lot of concerns here. The last one is sustainable trust. The industry, in some ways, is its own worst enemy for trust. They keep saying, well, we're going to save lives, but it's going to take hundreds of millions of miles to find out if that's true or not. And Waymo's, last I checked, only at 50 million, another 450 million or whatever to go before they have really statistically compelling evidence. What they say is robotaxis won't make stupid driving mistakes. Here's a full-page ad from Cruise saying humans are terrible drivers and our robotaxi will make sure nobody dies. That isn't quite what it says, but that's clearly intended messaging, and they just blame humans for making mistakes. Well, the problem is that it will take years, and each company has to do it on its own to prove that it's really true they're saving lives because there's not enough data yet. But every single newspaper photo of a robotaxi doing something stupid undermines the message of humans are bad drivers and we won't make stupid mistakes. Well, robotaxis make stupid mistakes all the time. And so as a public messaging approach, this is really a bad idea. I think instead they should focus on, hey, we're dependable, trustworthy partners, and of course we'll make mistakes, but we'll be very transparent and explain how we're fixing them, instead of saying, you humans are awful, we're going to be better than you, and then doing the same things. They also have some trust degrading actions. Some of these are kind of specific to the US, but basically they try and make it so no one can come after them if they make a mistake, and they withhold all the information they can. They're very, very opaque. I think we need to see more transparency on incidents and follow-ups. They're always blaming everyone except themselves, even when it probably was at least partly their fault. And I think that more transparency would help, and a little more humility, saying, yeah, we made a mistake there, but we're fixing it, would really make a big difference in increasing trust. And the other thing is, we don't know what criteria they use to decide. They say, well, our smart people figured out it was time to pull out the driver. And the fact that we're about to run out of funding is coincidental. And you've heard those kind of stories. Or maybe it wasn't. We don't really know. And so those kind of things would help. Some companies are doing a little better at that these days, but that's an industry kind of problem that needs to be worked on across all the companies. So we're about halfway through the talk. Let me sum up where we are. I said net statistical safety, safer than average driver. Yeah, that's table stakes. People think that's all of safety. It's just how you get started. And even doing that, there's like a whole book on how hard it is to do that baseline. But also, it's not okay to transfer risk away from the car passengers and impose it on other people outside the vehicle and make it dramatically less safe for them, even if the net number goes down. That's going to be a social problem. It's not going to be okay to drive recklessly and use the excuse we're saving lives, or our robotaxi is so smart it knows what the right thing is. It can ignore the same rules to apply to human drivers. That's going to be a problem when it gets in a crash, because it will have ignored the law while getting in a crash, and that's going to be a huge legal liability for the industry. It's not okay to have really, really risky individual behaviors and say, well, yeah, it'd be really hard to fix this, but we're saving lives, so you should give us some free fatalities to make up for it over here. And that's not going to work. It doesn't work for human drivers. It's not going to work for robotaxis. There will be recalls for that. And finally, there's a bunch of ethical behavior and equity concerns that if you get people really upset or you behave in an untrustworthy way when you have a crash, don't expect people to be sympathetic, and don't expect people to trust you when you say you fixed it if you've lost their trust and acted unsympathetically in the past. Okay, so let me move on. I think because we removed the human from the car, we need to change how we look at safety engineering. And the robotaxi experiences in San Francisco in particular give us a really good idea where and how. So I'm going to go, for those of you who are standards wonks, if you look at ISO 26262, it has a list of definitions that go up to safety, and I'm sort of invoking them and sort of rewriting them. I'm not rewriting them in a way that is incompatible. What I'm doing is I'm expanding the scope to say those definitions are fine, but just as net positive risk balance is only a piece of safety, those definitions are only a piece of safety. And so these definitions are compatible with, but more expansive, and address the issues that arise when there's no human who has to take charge. And so we're back to, by the end, you'll understand why I say this is a multi-constraint satisfaction rather than an optimization problem. Okay, now, historically, the way I got into this, when I was writing the proposal for UL 4600, so I wrote a big couple hundred pages of proposal that went in and then went through the standards process to be issued as a industry consensus standard. Something that bothered me was the definition of a safety case. And I'll come back to this, but it's a structured argument based on evidence in a given operating environment. And it always bothered me because it just something about it bothered me, and I didn't know what, and it took me several years, but now I know what bothers me about it. What bothers me about it is that if you have an airplane and the airplane's not supposed to fly in particular conditions because it's unsafe for the aircraft just can't take it, or the sensors won't work, or there's icing, or you don't have instruments and there's fog, those sorts of things, it's the pilot's fault for trying to fly in the bad weather. Okay, so we're delegating enforcing the operational environment for self-driving car folks, enforcing the ODD. We're delegating that to the person, but there is no person. The autonomous vehicle is supposed to figure out it's in an unsuitable environment and deal with it. So if you have a safety case that you're safe in a given operating environment and it's outside the operating environment, the safety case doesn't apply, but you still have to do something. And so this definition of a safety case does not guarantee safety if there's no human operator, because you want to operate in the given environment, but you have to be safe even if you're outside the environment. And so here are a couple examples. This is a Cruise robotaxi that crashed into a bus. Remember I said there were embarrassing pictures? You're going to see some of them now. This crashed into a bus. The sensors saw it, the LiDAR saw it, the camera saw it, everything saw the bus. There was no extenuating circumstance. It was a beautiful day. What had happened was it had been trained on 40-foot buses. And San Francisco has some 60-foot buses, and those 60-foot buses have a joint in the middle, so they bend. Okay, the back 20 feet or so bends compared to the front feet, and it decided to track a bus by looking at the front of the bus and measuring 40 feet back. And so it saw the bus and it said, that can't be the bus because I know buses are 40 feet long. It must be a sensor error. So it just ignored it and ran into it. So its given operating environment included only 40-foot buses. 60-foot buses were not part of its environment, so it hit one. So the safety case could have been perfectly valid, but the operating environment did not match the safety case, and there's no human operator to blame. So these are the kind of things that are going to show up that break the usual way of looking at safety. This is a Waymo that ran into a utility pole. This one's a little more subtle, but it knew about utility poles and it knew about curbs, and all the testing and validation they'd done had been with a curb between the car and the utility pole. It turned out that some things you have to label as okay to hit. If you can see that little scrap of plant down there, that plant is okay to hit. And they had accidentally, as a design error, tagged utility poles as also okay to hit, the same as that little piece of grass. And it had never been a problem before, because if the utility pole was behind a curb and you don't hit curbs, you would never hit the utility pole. Well, this utility pole does not have a curb around it, so they hit it. So a utility pole without a curb was in the real world, but was in amounts to not part of their defined operating environment. So this shows you that even the usual definition of safety case is kind of broken, because you still have to be safe even if the given operating environment is not where you are. So based on that, I think we need to expand the scope of safety, and all the other definitions have similar issues that I don't have time for to explain why they're a problem, okay? So robots can fail even though they don't drive drunk. You just saw them failing even though they weren't drunk. And these are the first half of the talk talked about sort of the issues you have, but really it boils down to there's no human operator blame, or there's no human operator responsible for avoiding negligent behavior, or for enforcing giving environment, for doing social interactions. All this stuff that people used to say was out of scope for safety standards is in scope now, because there's no driver to handle it for you. So let's take a look at revising the definitions. Now, this could get really wonky. I'm not going to read every single definition and parse it word by word. I'm going to give you the ideas. I'll have a definition at the bottom, and the very last slide will have all the definitions collected for people who really want to see them. And of course, the slides are available. And this is, there are a couple academic papers that I published that have all the details here. But in ISO 26262, which is the functional safety standard for cars, loss is, they talk about harm, physical injury to people. But there are things that matter other than hurting people for robotaxis. Here's a headline that this has happened twice now, that a robotaxi ran over someone's pet dog. And I'm not saying that a pet dog should be the same as a human life, but I have friends who have dogs and didn't have children, and those dogs are really important to them. And if the dog gets harmed, this is extremely traumatic. Running over a dog is not weighted as 0. It matters, especially if you care about social opinion. And so I think loss should be more than just harm to people. And many other safety standards go down the same path as well. ISO 26262 is the most restrictive in this. And it's any adverse outcome. And I don't care what it is, it's an adverse outcome, including negative social externalities. Now, I did not say they're all weighted the same. It's fine to weight some of these important. It's fine to weight some of these as low. Maybe you even weight some of them as 0 if you choose to do so. But you should consider all these adverse outcomes, and then you should have a definition of what a loss is with appropriate weightings for each category. If you don't put in a standard that these are all the categories that matter, then people will ignore them because they're in a hurry, they have constrained resources, and they say, well, the standard doesn't require it, so I'm not going to do it. So you really need a standard to say, these are all the things to consider. And loss is all of these things. For risk, classical risk is probability and severity. We also see patterns of losses, though. So I talked about recalls. There was a Tesla recall, 956 crashes and 29 fatalities for one recall. So the problem with the US system is it takes a lot of harm before some recalls happen. It's very reactive. A lot of bad things can happen before there's a recall. And they were based on basically automated emergency braking not really working the way it should have, loss of yaw control, so spinning out in wet conditions, and people would bump the steering wheel for driver monitoring and inadvertently turn off auto steer, and then they would crash. So this is the definition of risk is not just net statistical safety, but patterns of losses also matter for safety, and the recalls sort of prove that. So a risk is a combination of the probability of the occurrence of a loss or a pattern of losses, and it's not the harm. So risk is often basically boiled down to a dollar or euro amount. And it's not purely monetary. Remember about the dog who's run over. Well, a dog does not necessarily have a high monetary value, but it has a lot of value to the people who it's close to. And so importance to stakeholders is going to matter because how bad the headline looks can hurt the business, and it doesn't matter how much money the loss was worth. So importance to stakeholders rather than monetary value. Now, safety constraint. This is a new definition. We don't see this in standards, but safety is not just the net minimization of the sum of risks. And the reason this has been a problem for safety for decades is safety struggles with 0 probability times catastrophic consequence. Well, that's never going to happen, but if it does happen, a whole bunch of people are going to die. That there is tremendous organizational, financial, and other incentive to round that down to 0 risk. But then when it happens, your company goes out of business. And we've already seen this happen to a couple times in the self-driving car industry. We've seen this at play in the nuclear power industry. And so people get 0 probability and catastrophic consequence wrong. But we also have other risks that a design team should not be allowed to optimize. So there is, this is the retiring San Francisco fire chief. She has an article where she's really unhappy with the robotaxis. And one of the things they were doing was they were interfering with fire truck operation. They were blocking fire trucks, blocking ambulances, driving into fire response teams. In one case, a robotaxi pulled in between a fire truck and a burning car and saw something was wrong and stopped between the fire truck and the burning car. So they had trouble putting out the fire in the burning car, just making a nuisance of themselves. They were parking in firehouse driveways, blocking the fire trucks into the firehouse. And it's, how do you put a dollar amount or how many people are going to die because you blocked the fire truck when the fire entrance in that day was not the day the fire truck had to leave? But we don't tell automotive teams you should assign a dollar value to blocking a fire truck, and if it's cheap, it's okay to do it. You don't say that. You say you're not allowed to block fire trucks because that's the law. It turns out that when you are designing a robotaxi with no human in it, the computer has to be taught to follow rules, and the design engineers do not get to decide when to violate some rules or have to have a really strong justification for violating them. And it's not just boiled down to a sum of risks. Okay, so that's why we have regulations and rules and laws. Is there some actions you're not allowed to do even if you would financially benefit from them? And that applies to robotaxis too. So there's no single unique risk equation, multi-factor risk equation you can optimize to get the best risk. It doesn't work that way. There are constraints. You're not allowed to do A, B, and C. You're just not allowed to do it. In D, E, F, you're allowed to do it, but if you guess wrong, if you choose wrong, you're gonna pay very high consequences. And then C, sure, go ahead. You know, the last one, go ahead and optimize the risk. But it looks like a set of constraints of things that you have to not violate, and after you're done not violating any of them, then you can optimize risk. So a safety constraint is a limitation imposed on risk. Just like in businesses, you're not allowed to do insider trading even though you can make money. That's a regulation. The things cars are not allowed to do, even though that might benefit them in the small, because they cause too much societal harm. So it's a limitation due to stakeholder requirements, and you have to obey all the constraints. Okay. Almost done here. So safety engineering. Testing alone does not create a safe system. I argued that in the beginning, and it's because you need a strong prior expectation of safety by following standards. Testing alone doesn't get you there. Yet we see an industry that keeps saying, look at all of them million miles, we're at 1 million mile, 10 million mile, 50 million mile. And it's like, well, you need another factor of 10 more million miles, more or less, to prove statistical safety. And it's unlikely you're actually going to get that without a loss event. So you need 1 billion miles. Miles doesn't prove you're safe. A moderate amount of miles can prove you're unsafe if you have a crash, but lack of a crash just means we don't know yet, and they're nowhere near. So safety engineering can't be about testing. And by the way, when they say we have all these million miles, all the statistical safety approaches based on million miles assume the same version of software, and that software is changing all the time. So even if you get 1 billion miles, the software after 1 billion miles looks nothing like the software on the first mile. So I don't even know what the argument even means. There's some argument there, but it's not the obvious argument that people want you to believe. So I'm going to say safety engineering has to be based on a Bayesian prior belief of safety and not just look at all the testing we did, even if it's in simulation. So safety engineering is a methodical process. And I listed some things. Some folks might have a different list they want, and that's a great conversation to have. But if you're not identifying hazards and mitigating them, you're not doing safety engineering. If you're not doing safety engineering, you have no prior basis for believing you're safe when you go on the road. And that's the short version. Okay, so that finally gets us up to a safety case. Remember, I was unhappy with given application in a given environment because these things might be misused, and because the environment isn't necessarily the one you expect. In fact, it probably will never be the one you expect. You'll probably always be missing edge cases. So we need something else. We need to figure out who or what enforces the operational limits. We have to know what if the environment is unknowable in full, which for the foreseeable future is going to be the case. We have to deal with foreseeable misuse. So a bunch of folks, at least in the US, are going out and buying Teslas because they've been told it drives better than they do. And so they're driving drunk with it because they've been told it drives better than they do. So it must be safer to go home with it drunk than drive themselves home drunk and getting arrested or having crashes. And if you have a robotaxi, there are going to be other foreseeable misuses that you need to include in safety. All right. So any of these things are automated. Foreseeable misuse is a thing, and blaming the drivers won't stop the misuse. It won't achieve a safe outcome. You need to do a little bit more than that. So the safety case, and this is the usual definition, structured argument supported by body of evidence that provides a compelling, comprehensible, and sound argument that safety, but it's safety engineering efforts. You're not doing safety engineering, you don't have a safety case. And it's not that have acceptable risk or absence of unacceptable risk. It's that they meet a comprehensive set of safety constraints. One of the safety constraints could be net loss rates are low enough, but that's not the only safety constraint. Okay, so for acceptable safety, you have to meet the ethical constraints. You need positive risk balance, no negligent driving, no recallable behaviors. They meet the legal restrictions such as passenger drop-off, but you have to go to all your stakeholders, and it's more than the auto industry and insurance industry that gets a vote. Road users, consumer advocates, regulators, they all get a vote on what safety means. And it should be responsive to all these inputs, not just the car company says, yeah, it should be fine. The car company saying we're willing to take the risk doesn't mean that everyone else is willing to take that risk. So acceptable safety is it meets all the safety constraints as shown by a safety case. And so when I say that a self-driving car is safe or a robotaxi is safe, that is a shortened version of it has acceptable safety. And by acceptable safety, I mean all the things you just saw in the last few minutes. Okay, now wrapping up, I'm going to completely go off script here. If you're an engineer, this is what you want for safety. If you're a regulator, this is what you want for safety. If you're any one of the stakeholders, this is probably what you want for safety, for all the reasons, and hopefully I've convinced you there's more to it than positive risk balance. But if you are the general public, that is not how you're going to look at safety. People without a STEM education, people who have not spent a lot of time learning the industry and understanding how things work, are not going to think about it that way. People do not react to statistics very well. General folks do not have an education in statistics and are not particularly good at reasoning about statistics. It's a specialized skill that people who have the skill tend to forget that not everyone can think rigorously about 1 per billion. 1 per billion is literally beyond human experience. It doesn't mean anything. It's just a number. And if you don't believe me, have discussions about people about whether they think they're going to win the lottery. Okay. And the other thing is people are not swayed by statistics. They're swayed by stories. People make decisions based on stories. And that includes everyone in this meeting as well. We make decisions on stories, and we've been trained to pull statistics in to challenge our assumptions, but we all react to stories. So what if a reader of a news story says, I would never have made that mistake? Think about it. When you saw the robotaxi crash into a bus, what was your reaction? When you saw a robotaxi crash into the utility pole, what was your reaction? I mean, a typical reaction is we were promised they wouldn't drive stupid. And there's a picture of it driving stupid. I'm not sure about safety, okay? And so I have a hypothesis. Now, I'm an engineer, not a social scientist, so it's just my engineering hypothesis. But I think for each crash, the public is going to judge safety by whether they think they themselves would have made that mistake as a human driver. And if they said, oh, I would never have crashed into a utility pole, then that must make the robotaxi a bad driver. And that's a problem for the industry because this is setting the bar very high. Now, I understand from an engineering reaction is going to be, this is very unfair because I actually tracked down the paper that showed that something like 80% of drivers are sure they're above average, which you know, it's not a thing. It's they all overestimate their ability. And there's nothing like looking at what a mistake someone else made and telling yourself you would never have made that mistake, even if you totally would have made that mistake. Just people are optimistic about their abilities and optimistic about their about not making mistakes in a situation under stress, under tough conditions. But it doesn't matter because that's how people are going to behave. And so manufacturers have to keep in mind that even if they are positive risk balance, even if they're acceptably safe, that they're going to get judged on every bad optics outcome And earlier I said, I think that promising saving lives is really a bad mistake. This is why. They shouldn't be promising saving lives. They should say, sure, someday we'll save lives. But the reason you can trust us is that on a crash by crash basis, either we won't make a mistake a human would not have made, or we will be very transparent about, oh, that's what happened. Okay, now you can trust us that we will never make that mistake again. Okay, so wrapping up, I think we need new definitions for safety. This goes back to, yeah, we probably should revisit ISO 26262 if we're going to apply it to autonomous vehicles. I mean, it's probably fine as it is for conventional vehicles, but if you're in an autonomous vehicle standard, all these things have to show up in safety, because you don't have a human driver in charge of handling surprises in the environment or enforcing the operational limits or rules. Every rule is ambiguous. Every traffic rule has some element of do the right thing, and doing the right thing is not something that's easily encoded in rules. And there are legal and ethical constraints. All those have to be brought into safety, or we're not going to get acceptable safety for self-driving cars. And I don't think that we can reinterpret existing terms. People say, well, we're going to use ISO 26262 and adapt it to autonomous vehicles, and it's going to break partly for the slide I showed you, but also because lots of organizations are motivated to minimally comply with standards as a cost and time to market thing. And if we say you should reinterpret, if it's not in the standard, they're not going to do it. And I think the terms should say what they mean. So I really think we need a very big revision of safety standards, not just for cars, but for airplanes, for everything, to deal with autonomy, to deal with the fact there's no human operator, to take care of these things that were previously out of scope for the standard because we knew the human was there. There's a couple extended papers on this. There's a bunch of resources with more YouTube talks than you can stand, and there's a book. There's another book coming out in probably September that covers the material in this talk. There's a lot of stuff you can look at, but with that, I'm going to put up the definitions and we can switch over to questions. Thanks for your attention.
Thank you, Phil. So very, very insightful, and I think we learned quite a lot of things. So maybe we can start first by taking the questions that were in the chat. Anyone can, of course, raise his hand and then open the mic and the cam. So I really invite you to open the cam now, so it's much more fine for Phil to have people in front of him.
Okay, so here's one. Who is held responsible for a technical failure in a robotaxi? The manufacturer, the operator, the software developer? Is there a clear legal framework in place for California? It depends on the state. So I'll talk about US. In the US, there is no federal rule for who is held liable for a crash, because that's liability of state law. And in the states, the Autonomous Vehicle Industry Association has been busy, and others have been busy lobbying state by state. So there are different rules for each state. The last I checked, in Oklahoma, the computer is responsible for a crash, the computer. And so if it kills someone through reckless driving, apparently you pull the computer out and throw it in a jail cell and put in a new computer and everything's fine. I swear I'm not making this up, okay? And in other states, it's the owner, and the owner right now is the manufacturer, or is it? I mean, what if they leased it to some company that's doing the operations, and then that company serves to evaporate under a lawsuit to protect the manufacturer? I know of no state in which the manufacturer is going to be held responsible. All these state laws, there might be one, but I'm not aware of one. All these state laws are set up to make sure someone other than the manufacturer gets blamed for a crash. And that's clearly broken. Now, the Oklahoma law is obviously ridiculous. But my lawyer friends tell me that's the point. The point is to make it extremely expensive for someone to pursue a lawsuit and eventually get to the manufacturer, because the manufacturer is the only one who can avoid the crash, right? And so these laws are there simply to protect the manufacturers, not to actually equitably assign someone responsible. So our proposal is that the computer driver should be responsible and the manufacturer should be the responsible party for the computer driver. And if you did that, there's the 3 legal papers I mentioned. I'll give you an analogy. Back when electronic signatures happened, nobody knew if an e-signature was legal or not. If there's no ink on paper, no one knew it was legal. So all the states in the US passed a uniform law saying, guess what? if it's an electronic signature, and here's what we mean by electronic signature, but it's the stuff you guys all know, right? If it's an electronic signature, guess what? Everywhere in current law, it says signature. Yeah, that's what we mean. And so our proposal is everywhere in current law where it says driver, a computer driver is a driver, just like a human driver, except if you're going to give a ticket, it goes to the manufacturer because they're the only ones who have the ability to change it. And manufacturer is a little nuanced because if you buy a standard car and put a computer driver on top, the manufacturer is whoever put the computer driver on top, right? And that would bring the existing tort law framework in, so you don't have to prove a product defect, which will be difficult or impossible to prove in these cases. You can just say, hey, the robotaxi ran a red light and hit someone. If a human had done that, we'd be upset, right? Yeah. Okay, well, we should be just as upset, and the same thing should happen because it's a computer. That's the proposal we have. F says, even though positive risk balance is just table stakes, should AV type approval regulations at least state clear acceptance criteria to determine whether AV can be approved or deployed? So right now in state regulations, where we are is they ask, do you have insurance? Are the state police who have no technical expertise on computers happy that if they stop you or there's a crash, they'll be able to get hold of a remote operator, basically. And that's about it. Some states require you to operate with a test driver and not have a crash for 50,000 miles or 500,000 miles, depending on, for less than 1 million miles. As long as you can operate with a test driver without a crash for a few tens or hundreds of thousands of miles, you automatically have a driver's license. You don't even have to take a driver's test. Computers automatically get driver licenses by virtue of being a computer. And just go out on the road and see what happens. And in practice, even in California, which is the most rigorous, anyone who can put a car on the road that doesn't crash into things will get the permit if they have patience and have the discussions with California DMV. I mean, I know Miguel was on. He said what he said, and I'm not going to go. I'm not trying to contradict anything he said. But my opinion is, my observation as an outsider, is anyone who's competent can get the permit, and they operate until there's a crash. And then when there's a crash, the permit gets taken away. And that's where we are. Now, I would like to see something a little more technically rigorous, but how does a state DMV have the resources to do source code analysis of an end-to-end machine learning system? That's just not going to happen, right? So how do they do that? And the feds aren't doing anything about that. And by the way, historically, the federal government controls equipment, not the states. So there's a lot of questions there. I have a recent proposal, which you may have seen on I have a Substack, which if you're into this stuff, there's a lot of stuff there. I have a recent proposal that maybe what they should do is the regulators should do an audit of the safety case, not a technical evaluation, because that can be accused of being subjective and a bunch of other things, but an audit saying, hey, do you have a safety case? We're going to have somebody independent check and just make sure that, for example, all the clauses in UL 4600 have actually been addressed in the safety case. We're not going to judge you on whether we like it or not. Just if you can't even come up with a safety case that checks all the boxes, then what are you even doing, right? Now, that will not guarantee safety, for sure. Of course it won't. But it's just like a bank audit. Even though banks you can have fraud, you can keep a second set of books, you can lie on a bank audit. It takes a lot of work to do that. So that means it forces you to at least do enough rigor to have a set of books. And it sets you for more effort if you're going to deceive. And it sets up a record that if something bad happens later, there's a paper trail saying, hey, you guys were lying, and so now we can beat on you. So it's an incentive and a deterrence from bad effort because you know that you might be punished later. So I think that's sort of a halfway measure that is a process-based thing, but it's not really process. It's just, we don't tell you how your safety case has to be done. We don't tell you what has to be in it. We just tell you it has to address the following concerns. And I think I floated that idea out recently, and maybe we'll see something like that. I think the regulators have to do more than just say, do you have insurance? Okay, go on the road. And I think it's going to be decades before we can have road tests that are meaningful because the technology is still maturing. And those road tests take 5, 10, 15, 20 years to develop. We need something before then.
Tim, so I understand why Waymo claims to be safer are not enough. So what would you be the best statistic? I mean, what would be the best KPIs? You said that there shouldn't be any risk transfer to vulnerable road users and so on. So what would be the perfect KPIs, and maybe several KPIs that should be controlled, checked?
So Waymo, this is Tim had a question specifically about Waymo. Waymo prides itself on being the most rigorous about looking at safety, and that's a true statement, but it doesn't mean that they're doing everything they need to do. Both those things can be true at the same time. There's an important thing about Waymo. If you read the research papers, they will very clearly state they do not have nearly enough data to know about fatalities. Okay? But if you read their webpage, the last time I checked it, their public relations people are saying, we're saving lives today. And that's not true. They don't know if they're saving lives. They don't even have one fatality worth of data, let alone statistical significance of fatalities. And so the public messaging and the regulatory messaging greatly exaggerate. They basically misinterpret the data, whereas the researchers are trying to put out deliberate, reasonable interpretations of data. So it's really important to keep those things separate. That having been said, assuming that the Waymo data is accurate, and there's other folks who have problems with the data, I'm not going to go there. I haven't spent the time. There's some folks who are unhappy with the data. Waymo defends their data. Go talk to someone who's analyzed the data in more detail to get an idea. But what I'm not seeing is, in fact, the things like breakouts by vulnerable population. All the stuff I talked about. And I'll give you one mishap as an example. There was a Waymo situation in which a remote drive, the Waymo was stopped at a red light, but it wasn't sure it was a red light. It called the remote operator and said, hey, is this light red or green? And the remote operator said green, but it was really red. So the Waymo drove through a red light because the remote operator said it was green. And then a crossing vehicle who had right of way, it was a light motor scooter of some sort, wiped out. He didn't actually hit the vehicle because he was trying not to hit the vehicle that had jumped in front of him, and he wiped out and had injuries. So, those are the kind of things that's basically negligent driving. Harm was caused by failure to obey road rules, and we don't see that broken out separately. So I think that right now the industry doesn't have that much driving data. I mean, they have a lot, but not enough for statistical significance on fatalities. And so as we see the driving data, I think it will be important over time to break it into bins, as I've discussed. But the other thing we see missing is there's another Waymo paper talking about the acceptance test they do, but we don't see a lot that goes deeper. What I know of their standards conformance is that they don't do standards. Their initial safety report said, yeah, standards don't apply to us, is the short version. And so there's a lot of issues there. Their main public relations messaging is you should trust us because we put it on the road according to our own criteria and it's turning out okay, therefore we're safe. And that leaves them extremely vulnerable to even a single bad mishap invalidating their whole argument, right? They're right where I said, every bad photo degrades confidence, and their defense is we're really smart and we really care and we're trying hard. But that's difficult to defend against the bad photos. And let's say we're X times safer on small crashes, we're X times safer on injury crashes, but you have to really look at the data to know what it's saying. And even there, the data are statistically significant but thin.
Okay, great, thank you. So maybe I'll take William's question. So you said, Phil, that there's no one to control the ODD. No one on board doesn't mean that there's no one to manage the fleet. So there's not a lot of transparency about all the supervisors, remote operators, and so on. I mean, people who can take a decision. I remember when I was first in Phoenix 3 years ago, I was really disappointed because the second day, actually, all robotaxis were with safety operators. And I contacted Waymo and they told me, actually, this is because there's a hurricane coming and we may not take the risk to have all vehicles in the city if there's flood or anything. It was not the problem that you would not be able to manage the road situation, but if there's a lot of issues in the city, then our whole fleet will be completely lost in the city. And so they were really aware of the situation that the ODD could be changing. So what would you say about this control of the ODD in advance, or how to control that?
I think that's an excellent and very nuanced question. So great job, William. Thank you for the question. You may have noticed in the last couple of days, the video making the rounds of a Waymo driving into floodwaters and getting stuck. So I know that Waymo tries hard and they pay attention, but they're not perfect. But that's a great illustration for this question. There are two levels. There's the safety case level and the tactical level. At the tactical level, even though you've done all the things you said that your operations try and try and avoid bad situations, it is always possible to be outside your ODD instantly with no warning, and the robotaxi has to figure out it happened. So the cruise crash, nobody knew 60-foot buses were outside the ODD. It was just not even a thing anyone had thought of. And there it was, it crashed into one. So there will always be a sudden squall, a weird vehicle that's not in your design database, and a utility pole not protected by a curb, a dust storm. I heard from some trucking folks that they get brownouts in West Texas. It's like a blizzard, except it's mud. So there's or dust. Okay, so there's always something that's going to happen you're not expecting that shoves you outside the ODD. You do not have to keep operating, but what you have to do is something safe, even though you're outside your safe operating design. And so there's a technical discussion that I think ODDs are basically not defined, that concept isn't defined the way it really needs to be for safety. UL 4600 has an idea of ODD subsets, and you have the off-nominal ODD subset and the nominal ODD subset, and you get pushed out of the off-nominal, out of the nominal into the off-nominal, and that's where you do your risk mitigation. Okay, that's how I like to think about it. But that means the robotaxi or robotruck needs to realize it's been shoved out of the nominal ODD into this fallback ODD, and it has to react. Now, for sure, you can reduce the exposure to that, and you can reduce the number of stranded vehicles by saying, we don't operate in hurricanes, and I see a hurricane coming. What say we don't operate today? I think that's a great idea. And that will mitigate the risk to a large extent, but you need more than that because it's always possible to get caught by surprise. So you need both of those things. And so in the safety case, the safety case is going to say, well, what are you going to do about enforcing the ODD? And it's going to say, well, we're going to catch most of it with our operations center saying don't drive in conditions that are likely to be off ODD. But then there's going to be another piece saying, and the vehicle is pretty good at deciding it's out of ODD by surprise. And maybe stopping in the middle of the road is okay if it only happens once a year to each car, right? It's a numbers game at that point. But you can't just say we're going to keep driving in the rain because the operations center was supposed to tell us it was raining and we didn't get the message, or it was a surprise. You can't do that. You have to have both. So great question. Thanks for giving the chance to have that little chat.
Okay, great. Darjan has a question about the utility pole you mentioned. How can you be sure that this is not going to happen in the future, and what would be the statement then for the general public? So I don't know if you see the question.
I don't see it, but that gets me there. So the thing is, the robotaxi companies are messaging, we don't make stupid mistakes. And they're going to make stupid mistakes, or people are going to say, well, I would never make that mistake, therefore it's a stupid mistake. And so it's just a self-defeating messaging. They should say, we're statistically having fewer crashes than human drivers. We're not perfect. Nobody's perfect, but unlike humans, we can learn from our mistakes. Here's a mistake. Here's why it happened. And we're not going to blame everyone else because, we were actually kind of to blame for this one. Okay. We're kind of to blame, and here's what happened, and here's why it happened, and not, oh, we fixed the bug. Fix the bug. Oh, give me a break. That just means all the rest of the bugs are there. No. We found out that the reason this happened was he had a review process, and the review process had this hole in it. So we fixed the review process, and we reviewed every other object we know about to make sure we didn't have the same mistake. That kind of argument is going to build more trust. Now, that's an engineering argument. I get it. But even for the general public who doesn't know about engineering, if you say, yes, there's this little symptom, but we're not going to treat the symptom. We're going to treat the underlying cause. Here's the underlying cause. Here's how we treated it. If you say, well, we put a Band-Aid on it. Well, yeah, fine. Good for you. I still don't trust you. You need to build trust. And so that's how I go at these things.
Okay, great. I think Darjan raised his hand, but you answered the question perfectly. So I had personally a question about the situation in China. Do you see any difference between Europe, the US, and China regarding those safety cases? What you have heard about Rewrite on Pony, AutoX, and so on?
I don't have a lot of insight into the safety case situation in China. I know that that 10 years ago, nobody was talking about safety cases. And now everyone's talking about safety cases. And I like to flatter myself and think UL 4600 had something to do with that. But everyone's talking about safety cases. And the question is, well, by safety case, do you mean a glossy brochure that waves its hands with pretty pictures, or do you mean something really substantive? And that's the question you have to ask, right? So I don't know what the situation is in China is. I know that there's interest from China as well as Japan, as well as EU, as well as from UK. I know all these. I know that lots of folks in US talk about safety cases, which is great. I do know that China just recently pulled back on supervised automation after a big crash. And I know that all along, or at least everything I've seen, is that every China robotaxi has a driver with a steering wheel and a screen watching at 100%. So they're basically operating as remote supervision for their robotaxis. And I think that's smart. I mean, there's a lot of problems with remote supervision. I get that. It's better than not having remote supervision. And what we saw in the Cruise robotaxi mishap, this is the one where the Cruise robotaxi dragged a pedestrian. It's a very complicated thing. I have a whole talk and paper on it. But the part that's relevant for here is the robotaxi moved without giving the remote operations a chance to jump in and find out what happens. And the remote operations, if you get a call and you go in and it's like, what the heck is going on? It's going to take you a minute to orient. And it waited a fraction of a second before it rolled. So if the remote operator had been continuously monitoring, they would have slapped the red button probably before it ever moved to say, something bad happened, I'm immobilizing until we sort it out. And so the lack of that continuous remote operation had a large effect on Cruise going out of business is what it boils down to.
Okay, great. Last question from the chat. So Tamash is asking about the digital twins and the simulation miles. What's your opinion on this? Could you refer it to your V model somehow? Right. Is it only machine learning, or is it something a bit different in the engineering process?
Fair enough. So one of the simplistic arguments is, well, it takes 1 billion miles to brute force, so we're going to do 1 billion miles of simulation. We are going to brute force testing. We don't need a prior expectation because we brute force. What that does is that says, well, the reason that could work is our simulation is a completely accurate representation of the real world, not only in physics, but also at 1 billion miles, you're seeing edge cases. And that means all the edge cases have to be into the simulation as well. And so what you've done is you've changed a problem of validating the robotaxi to a problem of validating the simulation. Now, that may be a smart economic move. Certainly, simulations are cheaper than doing robotaxi miles, so that's great. But if you say, well, we're going to do 10 million robotaxi miles and we're going to do 1 billion simulation miles, now I have to ask, well, is the simulation accurate? And it's not just, is it a physics accurate? In particular, does it contain all the rare high severity events? Remember I said rare and high severity is where safety has problems? Does it have enough rare high severity events to make sure that the outcome from the simulation will be predictive of real world outcomes? And is it communicating with your software stack in a way that the software stack is not learning weird artifacts about the simulation? You know, maybe I'll make up an example. This is a classic machine learning thing. I'll just make up an example. That maybe everyone on your test track is wearing a red hat. And so it learns people have red hats. And it does nothing about people don't have red hats, right? That's the kind of mistakes machine learning makes. And so what mistakes like that are in your simulation? And it's really hard to know. So simulation could do it. And certainly the end-to-end folks who want to use end-to-end machine learning to come up with synthetic simulations are betting this will work. But it's a real unknown whether that's going to be a sufficient replacement for the brute force testing. So it's an engineering rigor approach that I simulate so I don't have to test. I get that, but you've just basically done a recursive call down into, but now I have to prove my simulation is safe. And by the way, that's now life critical code where simulations didn't used to be. And life critical code, are you following all the life critical software standards? Are you doing all these things? No, you're not. And so it's hard to know how much confidence you can really put in that stuff.
Great, thank you. So Dario, you had raised your hand. Maybe you want to proceed?
Yes, but indeed I wrote it in the chat. I only wanted to, because I was reacting to what Phil was saying a bit earlier about the supervisor for the robotaxi in China. from what I understood, they now allow one supervisor for up to 15 cars. So yeah, once again, I think the impact or the ability of the supervisor to actually act on those cars when they have to monitor 15 different cars can be quite tricky, I guess.
Well, they started at 1-to-1, and then they said
Yeah.
1-to-3, and I had not heard 1-to-10 or 1-to-15, but that's not a surprise because they say, well, we drove 1 million miles and nobody had to jump in, so now it's 1-to-2, now it's 1-to-3, and the problem with one, and I sort of at the time predicted. So thank you, Fredaria, for letting me know they got there. But I predicted a problem like you're supervising 15 cars. What if 2 of them need help at the same time?
Exactly.
And can you effectively supervise 15 cars, right? So we end up being at the. This is not what they're saying, but eventually end up at a call center model where the car calls in for help, right? You say, you know, I'm sorry, all our operators busy. We'll attend to your crash as soon as it happens. I mean, these are the kind of thing, when they say they have remote assistance, these are kind of dynamics I worry about.
Yeah.
One of them is a call center model that queuing theory doesn't help with the outliers. And if you have a power outage, all the cars are going to need help at the same time when the traffic lights go out, for example. Maybe not, but you know, there are things like that. And the other one is if you have a high fan out, one supervisor on a lot of cars, there's a lot of ways that can go wrong.
So thank you so much. I think it was very interesting for everyone. So as we said when starting, so we will publish. So I don't know, Phil, if you can already say if we may publish it on the YouTube channel.
Yeah, I think we're good.
We're good. Okay.
You never know. You never know what's word's going to happen. Believe me, I have stories, but I think we're good to publish this. Yeah.
Okay, amazing. So we'll try to do it as quick as possible. So if you want to share with colleagues and so on, and or to re-watch, it's no problem. So thank you so much for attending this webinar. So do not hesitate to send us a message if you have any question. We'll make also a report about what we will experience this week in Paris. We also have a conference that will be recorded and put on our YouTube channel as well. And if there's anyone interested in the study tour we do in China, do not hesitate to contact us as well. We'll organize another one in Luxembourg to try the Pony AI robotaxi, probably somewhere in September or October. And for the rest, thanks for joining. And Phil, we wish you a great day.
Thanks for having me.
Thanks,
everyone.
Yes. Bye-bye. Have a great day. Bye-bye.
Bye.